Hello everyone, it's Miss Thomas, and today we are going to learn about graphing rational functions. So, rational functions are any functions of the form f of x equals p of x over q of x, where p of x and q of x are polynomials. And the domain, so the x values, are all real numbers except where your denominator, q of x, is equal to 0. So basically anything that makes that denominator undefined. So we're going to talk about points of discontinuity. Discontinuity is any skips in our graphs, so things like asymptotes and holes. They're values that make the denominator equal 0. So we're going to be looking for those points that make it undefined. And we have two kinds of points of discontinuity. We have a removable discontinuity. And this results from a factor in the denominator that can cancel. And it will look like a hole in the graph. So an example of this, if you had f of x is equal to x plus 2 times x minus 1 over x plus 2. So we know that x could not equal negative 2 because it would make it undefined, but we can also see that clearly the x plus 2 cancels out. So our function will simplify to x minus 1, where our x cannot equal negative 2. And to graph the function, the graph is actually going to look, the graph for this is actually going to just be exactly the same as the graph of x minus 1, which is just a line. It's just going to have a hole where x equals negative 2. So we know our y-intercept is going to be a negative 1, because when y equals mx plus b, our slope is 1. So we have these points all the way along. Going back towards my point of discontinuity, when x equals negative 2, we're going to skip it. So your graph will be this straight line with a hole where x equals negative 2. And that's what the graph of a rational function with a removable discontinuity looks like. We're going to look at what happens when we do not have a removable discontinuity. So a non-removable discontinuity occurs at a value that makes the denominator undefined. But does not cancel. Okay? And at those points, you are going to have a vertical asymptote. If I have something that looks like f of x equals, we're going to need to talk more about the numerators, but some value over x minus a. Well, x minus a is going to result in a non-removable discontinuity. And whatever your value of a is going to be a vertical asymptote. We're going to need to learn a couple more things before we can graph anything that looks like this. So, horizontal asymptotes. There are three things we need to consider with rational functions to decide if they are going to have horizontal asymptotes. You need to keep in mind that m is the degree of the numerator. And n is going to be the degree of the denominator. And these are the values that we want to consider to decide if we're going to have a horizontal asymptote or not. So there's three different ways to decide. The first, if your m is less than your n, then you'll have a horizontal asymptote at y equals 0. If your m is greater than your n, then you don't have a horizontal asymptote. And if your m equals your n, then your horizontal asymptote is at y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. Okay, so let's look at a couple of examples of all of these scenarios so that you have a better idea of what we're talking about here. So scenario 1, where your m is less than your n, is going to be a function like y equals x minus 1 over x squared plus 4x plus 4. So if we compare our degrees, the degree of the numerator is 1, the degree of the denominator is 2. The degree of our numerator is smaller than the degree of our denominator, so that means the horizontal asymptote is going to be y equals 0. Looking at scenario 2, m is greater than n. Just imagine we had the reciprocal. If it looked like this instead, comparing those denominators, since the one on top is larger, then there's no horizontal asymptote. And our final scenario when we compare these exponents, they're the same. So the leading coefficients are 1 and 4. So the horizontal asymptote is going to be 1/4. Okay, so kind of putting everything together to graph these things. You're going to identify your horizontal asymptotes. You're going to identify any points of discontinuity and either make them asymptotes or holes in your graph. You're going to identify the x-intercepts by evaluating for where x equals 0, because, the y-intercept happens where x equals 0. And you're going to identify your x-intercepts by solving for the equation where y equals 0, because the x-intercepts happen when your y is equal to 0. Okay, so we are going to graph this. Step 1, we want to figure out our horizontal asymptotes. And we do that by using those rules. And we're looking at the degrees of our function. So we have a degree of 1 in the numerator and a degree of 2. So our degree of our numerator is equal to our m, which is equal to 1 in this problem. The degree of the denominator is our n, which is equal to 2. Our m is less than our n, therefore we're going to have a horizontal asymptote at y equals 0. So I'm going to get this graph going over here. So y equals 0. Is our graph. So we know we got a horizontal asymptote there. I'm just going to kind of put that dotted line on top. The next thing I want to do is identify any vertical asymptotes. And we do that by thinking about where's the denominator going to be undefined. So we're going to want to go ahead and factor that denominator. So x plus 3 over factors of 5 that add up to a negative 6 are going to be x minus 5 and x minus 1. So x minus 5 and x minus 1, x equals 5 and x equals 1 are both going to be vertical asymptotes because they're both values that make that denominator equal 0. They don't cancel out with the numerator. So I'm going to find where x equals 1. A little bit hard, sorry. X equals 1. And then where x equals 5, 2, 3, 4, 5. Wow. Sorry, having some technical difficulties there. Let's try that again. X equals 5. So we now have two vertical asymptotes. You won't always have that, but sometimes you will. All right, our next step is to identify our y-intercept by plugging in a 0 for the x. So y is going to be 0 plus 3 over, I'm going to use the factored form here, 0 minus 5 times 0 minus 1. So it is going to be 3/5. So I'm going to go on my y-axis, and it's going to cross about right there. this up a little. Then, to do my x-intercepts, I'm going to put a 0 in for my y and solve for my x. So the nice thing about finding your x-intercepts is that, oops, sorry. You really just need to solve the numerator, because when you multiply both sides by the denominator to cancel out, zero times all of that is going to be 0, and this is going to cancel. So you're going to have x minus 3. So your x-intercept is going to be a positive 3. So 1, 2, 3. Sorry, my intercept got, or my asymptote here got moved over somehow. So I'm just going to tweak that a little bit. That is not on x equals 1. And we want to make sure that it is. So I'm just going to redraw that. Okay, so now you may be thinking, well, what the heck do I do for the rest of the graph? So those are the things we really need to make sure that we're totally accurate on. After that, we can use technology, a table of values, to help us estimate the rest of the graph. But be very careful. Your calculator is only as smart as the operator. So when you use your calculator, you're going to want to really make sure that you're using parentheses like crazy. Whoops. So when you enter it in to your y equals, you need to make sure that you have parentheses around your numerator and parentheses around your denominator, because otherwise it's just going to take 3 divided by x squared and you're going to get some whacked out graph. So you need to make sure you have parentheses so that your calculator knows this is the entire numerator and that's the entire denominator. So then we're going to hit graph. Oops, nope, first we're going to hit delete because we accidentally hit that. So you can see our graph, our asymptotes aren't graphed on our graphing calculator, but this is where our vertical asymptotes are. Here's where our horizontal asymptote is. So you need to make sure that you come up and go down on either side of those two, and then there's this U on the bottom. So we can estimate those so that our curve is going to look like this. Oops, it's going to approach the asymptotes here and here. And have this parabola. Generally, when you have two vertical asymptotes, you'll see a parabola in between there, but sometimes you might see a slightly different pattern, so be careful about that. And that is it. I'm not going to give you a U-try. We will go over lots of examples of these, but the main things you need to be able to do are identify those vertical and horizontal asymptotes, the y-intercepts, and the x-intercepts.